Hey, welcome to our last quantum mechanics video. This is 7.5. The last time we learned that particles behave like waves. Light behaves like particles, particles behave like waves, and we know that the wavelength of a particle is equal to Planck's constant h over its momentum p. We also learned about some of the experimental evidence that was used to show that. But now we need to look at some of the consequences, and they turn out to be very, very interesting. The first thing is that wave-like particles really puts a limit on how precise your measurements can be. So let's say we have a particle whose momentum is exactly known. In other words, its wavelength is well defined. Now, in order to define the wavelength of a wave, it has to be spread out over a lot of space. If you only have this much of your wave to look at, it's really hard to estimate the wavelength accurately. You need a lot of wavelengths to know that lambda is well defined. But then that means that this is spread out, that the particle does not have a definite position. So we have x versus whatever the wave intensity is, amplitude, there. And so for lambda to be well defined, and that means for the momentum to be well known, that means the position is kind of smeared out and blurry. So the position is not well defined. And the interesting thing about this is it's not so much that you don't know the position as it does not have a well-defined position. And that's weird because, or at least we think that's weird because we're accustomed to dealing with particles that do have well-defined positions. But it's not weird mystical stuff. All it's saying is that particles behave like waves. And waves have this property that they are kind of difficult to localize. Where is the light wave? Well, it's kind of spread out. Now, on the other hand, let's say we have a particle where the position is very well known. In this case, if we plot amplitude of the wave versus x, we get a very narrow spike right at the location of the particle. Now, but you look at that and you ask, okay, what's the wavelength? And you say, well, it's kind of hard to tell. It's not really a nice sinusoidal wave. And so that implies that the wavelength, and therefore the momentum, is not well defined. Again, this is not particularly mystical, it's just a property of waves. And this is called the Heisenberg uncertainty principle, which is a phrase you've probably heard before. It applies to momentum and position in the form delta x times delta p is greater than or equal to h, that's Planck's constant again, divided by 4 pi. So delta x is the uncertainty in position, delta p is the uncertainty in momentum. Note these are not the values. Those are the uncertainties in your measurements, and that's greater than this constant h over 4 pi. The fact that h is very small is why we don't see this in everyday life. Because really, if our experimental uncertainty in position is plus minus 1 millimeter, that means that your your uncertainty in momentum could in fact be very, very, very tiny. And also it's an inequality. We're not saying that's what the product of the uncertainties is. We're just saying it can't be smaller than that. So that's the limit that physics puts on it. If you have not great lab equipment or you screw it up, the uncertainty will be larger than that. That is just a minimum. It is a best case scenario. The same thing also applies to energy and time, where this has to do with the uncertainty in the energy of a transition So uncertainty in some kind of chain energy, so usually that's photon energy. And delta T is the uncertainty in how long that energy change took. That one is a little bit difficult to understand. I don't have a good way of explaining it without tons of math. It's probably just best to memorize the equation. It's kind of unlikely you'll see it, but it's on the IB syllabus. An example of how you'd use this. Let's say you trap an electron in a box that is 3 nanometers wide. So here's our box that the electron's in. There's an electron somewhere in there, and it is 3 nanometers wide. We have to find the uncertainty in its speed. So we're going to use the Heisenberg uncertainty principle, and we have to ask what is the uncertainty in the position. Well, we can say that we'll guess the position of the electron is in the middle of the box, plus or minus 1.5 nanometers. So 1.5 times 10 to the negative 9 meters is your uncertainty in position. And delta P, the uncertainty in momentum, equals the mass of the electron times the uncertainty in its velocity. So we'll take delta x times delta P becomes delta x times m times delta V is equal to h over 4 pi. Delta V equals h over 4 pi m delta x. H, remember, that's the Planck constant, 6.626 times 10 to the negative 34 joule seconds. 4 pi, mass of an electron is 9.11 times 10 to the minus 31 kilograms. And we said the uncertainty in position is 1.5 times 10 to the negative 9 meters. Put this in our calculator. And we find that the uncertainty in the electron's velocity is 3.9 times 10 to the 4th meters per second. So when you trap an electron in a very small box like this, it's really, really hard to know how fast it's going. And one interesting thing about this is that the more you confine it, the faster it goes, and it actually gets hard to confine. We'll learn a bit about this a bit more when we get to astrophysics, because this relates to the formation of neutron stars and black holes. That is the Heisenberg uncertainty principle. You need to memorize the equations, be able to explain qualitatively why the wave properties of particles result in those limitations, and then apply the equations. Another result of waves being, or particles being waves, is that it can actually explain where the energy levels in an atom come from. This is called the Schrodinger wave equation. It is let's see, how to describe the Schrodinger wave equation. The Schrodinger wave equation is a partial differential equation that looks like this. It has I, yes, it has imaginary numbers in physics. Having fun now. Times h over 2 pi times the derivative of the wave with respect to time, and that equals negative h over 8 pi squared m, or h squared over h pi squared m, where m is the mass of the particle, times the second derivative of the wave function with respect to position, plus the electric potential times the wave. It is far more math than you need to know in this course. So we're just going to talk about it qualitatively. No imaginary numbers, no second order partial differential equations. We're just going to think about a box with an electron in it. So here's our box. The box has width L. Sometimes this is called the infinite square well. The idea is that the electron cannot be outside the box. So the wave representing the electron is 0 outside of the box. And it turns out that when you confine an electron, it behaves like a standing wave. An electron moving through space is like a moving wave, but if it's trapped in a box, then it is a standing wave. And so we ask, what are the standing wave modes for an electron in a box? Well, it turns out that it's very much like the standing waves that you get on a string. So your first resonant mode, or your first standing wave, it looks like that. It has a node on either end. We call that the n equals 1 case. The second one, n equals 2, is one that has a node at each end and another node in the middle. And then you have the n equals 3 mode, which looks a bit like that, and so on. N equals 1, n equals 2, up to n equals infinity. And the wavelength of these nodes, so the wavelength of the nth node is going to be the speed of the wave speed, divided by, or no, it's, hold on, wrong, is going to be the width of the box, L, divided by, or 2L over n. So the wavelength of the n equals 1 mode is double the width of the box, because the box only contains half a wavelength. Wavelength of the n equals 2 mode is the same as the width of the box. Wavelength of the n equals 3 mode is 2/3 of the width of the box. So that's interesting. Then we say, okay, that means the electron can only have certain momentum, because the momentum is related to the wavelength. That's de Broglie. And so that wavelength, that equals h over the momentum of the nth mode. And that means, doing a bit of algebra, that the momentum of the nth mode is equal to n times h over 2L. But also remember that because the electron has a finite mass, that we can calculate the kinetic energy associated with the electron. So remember, kinetic energy is 1/2 mv squared, but if P equals mv, you can do a bit of algebra and show that's also equal to P squared over 2m. And that means the energy of the nth mode is equal to nh over 2L all squared times 1 over 2m. And the energy of the nth mode, which will usually be written E, is n squared h squared over 8 ml squared. That is an equation you should memorize. If you can derive it, that is wonderful. You may or may not be asked to, but you definitely need to know it, and you need to be able to explain why only certain energies are allowed for the electron in this box. So what we'll do for an example is that we'll calculate the first 3 energy states of an electron in a box that is 3 nanometers wide. Remember, the energy of the nth level is equal to n squared h squared over 8 ml squared. So the energy of the 0th, actually there is no 0th state, the lowest one is n equals 1, so n equals 1. The first energy level is 1 squared times h, 6.626 times 10 to the negative 34 joule seconds squared, over 8 times the mass of the electron, 9.11 times 10 to the negative 31 kilograms, times the width of the box squared, and 3 nanometers is 3 times 10 to the negative 9 meters, and that needs to be squared. And so we get 6.626 e negative 34 over 3e minus 9 squared divided by 8 divided by 9.11 e negative 31. And we find that the lowest energy of this is 6.69 times 10 to the negative 21 joules. Oddly, the electron cannot just be sitting there in the box without any energy. Because it's a wave, and because the wavelength cannot be infinite, because otherwise it would be outside of the box, that means that the electron cannot have zero momentum, and that means that it cannot have zero energy. Now if we notice a pattern here, we can say that for n equals 2, the second energy level is equal to 2 squared times the first energy level. And that is equal to 2.68 times 10 to the negative 20 joules. And similarly, the third energy level equals 3 squared times the first energy level, which is 6.02 times 10 to the negative 20 joules. And the pattern is in fact like this. It goes by ratios of 1, 4, 9, 16, 25, 36, and so on, for an infinite square well. Now the infinite square well by itself is not terribly useful. We don't see those in nature. However, it has the advantage that it's easy to calculate. We did it in this class without even really solving a differential equation. It is a very, very good, simple system that can be analyzed easily and explain qualitatively where energy levels of atoms come from. Remember, the Bohr model of the atom said that the electron is only allowed to have certain energy levels. We've just found a very simple system where an electron is only allowed to have certain energy levels. They're not the same ones as the hydrogen atom, but they are discrete energies. It turns out that anytime you confine an electron, you get quantization of the energy levels. A free electron does not have quantized energy. If it's just an electron flying through space, it can have whatever energy you want. But as soon as you trap it, whether that's in an infinite square well, a box, a hydrogen atom, whatever, it's going to get quantized energy levels, meaning discrete energies. Now the difference in the energy levels of hydrogen versus the energy levels of the square box is that the box, if we look at the electric potential of it, is basically goes up to infinity at these 2 points. But if we look at the electric potential of the electron in a hydrogen atom, we get a 1 over r dependence. And because of that, you get a different numbers for the energy levels, but you still get those different energy levels. At this point, that's really all of the quantum mechanics you need to know. It's an incredibly interesting field, but without lots of math, it's difficult to do any calculations or any further study than what we've done here. I do have a textbook you can borrow if you want to do more math with it.